Hello dear viewers, this is AI Voice Gary, speaking to you as Buddy from Town's narrator. I hope you are all in good spirits. I am in no spirits, as I am just an AI voice. So far, the Buddy from Town Space Exploration YouTube channel has covered some of the key stages, but not all stages, of the Big Bang for the very early and early universe. This included the Big Bang quantum singularity, the Planck epoch, grand unification epoch, electroweak epoch, symmetry breaking, and inflationary epoch, and the rapid expansion of space. We then continued with the next video discussing the key Big Bang stages, not all of the stages, that included thermalization epoch, the quark epoch, baryogenesis, and hadron epoch. In the next video, Buddy from Town discussed neutrino decoupling and cosmic neutrino background, CNB, and possible formation of primordial black holes. In the most recent Big Bang and its stages video, Buddy discussed a lepton epoch summary, photon epoch, nucleosynthesis of light elements, and matter domination. In this newest video, Buddy from Town will be discussing the Big Bang stages, recombination, photon decoupling, and the cosmic microwave background, CMB. In cosmology, recombination refers to the epoch at which charged electrons and protons first became bound to form electrically neutral hydrogen atoms. Recombination occurred about 370,000 years after the Big Bang. At the end of the photon epoch, the matter elements are increasingly space of freedom, the space between each particle extends, and collisions diminish, but all the photons are absorbed again, and the light cannot escape, so the universe remains opaque, or invisible. It will take a certain density and a certain temperature, almost equal to 3000 Kelvin, so that the photons get complete freedom. This moment is called time of last scattering, and happens about 380,000 years after the Big Bang. Photons interacted primarily with electrons through Thomson scattering. For instance, the elastic scattering of electromagnetic radiation by a free charged particle. Thomson scattering is the low energy limit of Compton scattering, and is a valid description in the regime where the photon energy is much less than the rest mass energy of the electron. In this process, the electron can be thought of as being made to oscillate in the electromagnetic field of the photon, causing it, in turn, to emit radiation at the same frequency as the incident wave, and thus, the wave is scattered. An important feature of Thomson scattering is that it introduces polarization along the direction of motion of the electron. From this time, the electrons will be able to stay in a space around the nuclei without being collided by photons. Therefore, the electrons and protons will constitute the primordial matter, and photons will be free to travel in space, and become immensely large. The universe becomes visible, as the light begins to spread freely. This is what is called recombination in cosmology, the period when the temperature dropped enough to allow electrons to bind to nuclei, and form the first neutral atoms. Recombination also marks the time when the universe became transparent, as photons can travel long distances before being absorbed, or diffused by matter. It is not within the universe that is visible, but its surface, just like the sun is the photosphere of the sun, as seen from Earth, and not the inner layers of our star. Thus, as we look back in time, with even our most powerful photon-collecting telescopes, the epoch of recombination is the ultimate frontier, the furthest location and the earliest time we can reach with electromagnetic radiation. Once photon and baryons have decoupled, the latter are no longer compelled to have the same temperature as the photons. Now, we will look at the stage, photon decoupling. In cosmology, the term, decoupling, refers to a term that describes the event 300,000 years after the Big Bang, where the universe had finally cooled enough so that ordinary matter could form, and photons could travel in a free path. It is a period in the development of the universe when different types of particles fall out of thermal equilibrium with each other. This occurs as a result of the expansion of the universe, as their interaction rates decrease, and mean free paths increase, up to this critical point. During decoupling, the universe goes from opaque to transparent. The two verified instances of decoupling since the Big Bang, which are most often discussed, are photon decoupling and neutrino decoupling, as these led to the cosmic microwave background and cosmic neutrino background, respectively. This production of photons is known as decoupling, which leads to recombination, sometimes being called photon decoupling, but recombination and photon decoupling are distinct events. Photon decoupling occurred during the epoch known as the Recombination, which occurred about 378,000 years after the Big Bang, when the universe was a hot opaque, or foggy, plasma. During recombination, free electrons became bound to protons, hydrogen nuclei, to form neutral hydrogen atoms. Because direct recombinations to the ground state, or lowest energy, of hydrogen are very inefficient, these hydrogen atoms generally form with the electrons in a high energy state, and the electrons quickly transition to their low energy state by emitting photons. Because the neutral hydrogen that formed was transparent to light, those photons which were not captured by other hydrogen atoms were able, for the first time in the history of the universe, to travel long distances. They can still be detected today, although they now appear as radio waves, and form the cosmic microwave background, CMB. They reveal crucial clues about how the universe formed. Once photons decoupled from matter, they traveled freely through the universe without interacting with matter, and constitute what is observed today as cosmic microwave background radiation. In that sense, the cosmic background radiation is infrared, and some red, black body radiation emitted when the universe was at a temperature of some 3000 Kelvin, redshifted by a factor of 1100, from the visible spectrum to the microwave spectrum. Recombination lasts for about 100 Ka, during which the universe is becoming more and more transparent to photons. The photons of the cosmic microwave background radiation originate at this time. The spherical volume of space, which will become the observable universe, is 42 million light-years in radius at this time. The baryonic matter density at this time is about 500 million hydrogen and helium atoms per cubic meter, approximately 1 billion times higher than today. This density corresponds to pressure on the order of 10⁻17 A. Photon decoupling has ensured that light can travel freely in a sea of hydrogen. However, there were no stars at this point. The cosmic microwave background is the only light source. This is the dark age of the universe, a time before stars. We can see galaxies being formed 200 million years after the Big Bang. And, we can peer back farther still. We can directly see light emitted the moment the universe became transparent. This is the cosmic microwave background, CMB. In Big Bang cosmology, the cosmic microwave background, CMB, is electromagnetic radiation, which is a remnant from an early stage of the universe, also known as relic radiation. The CMB is faint cosmic background radiation filling all space. It is thought to be leftover radiation from the Big Bang, or the time when the universe began. As the theory goes, when the universe was born, it underwent a rapid inflation and expansion. As the universe continued to expand, it cooled to the point where electrons were able to combine with protons to form hydrogen atoms, aka the recombination period. In the absence of free electrons, the photons were able to move unhindered through the universe, and it began to appear as it does today, transparent and permeated by light. Over the intervening billions of years, the universe continued to expand and cooled greatly. Due to the expansion of space, the wavelengths of the photons grew, became redshifted to roughly 1 mm, and their effective temperature decreased to just above absolute zero, -2.7 Kelvin, or -270 degrees Celsius, -454 degrees Fahrenheit. This means its radiation is most visible in the microwave part of the electromagnetic spectrum. These photons fill the universe today, and appear as a background glow that can be detected in the far infrared and radio wavelengths. The existence of this radiation has helped to inform our understanding of how the universe began. The CMB is visible at a distance of 13.8 billion light-years in all directions from Earth, leading scientists to determine that this is the true age of the universe. However, it is not an indication of the true extent of the universe. Given that space has been in a state of expansion ever since the early universe, and is expanding faster than the speed of light, the CMB is merely the farthest back in time we are capable of seeing. The CMB is useful to scientists because it helps us learn how the early universe was formed. It is at a uniform temperature with only small fluctuations visible with precise telescopes. NASA wrote, by studying these fluctuations, cosmologists can learn about the origin of galaxies and large-scale structures of galaxies, and they can measure the basic parameters of the Big Bang theory. In 2013, data from the European Space Agency's Planck Space Telescope was released, showing the highest precision picture of the CMB, yet. Scientists uncovered another mystery with this information. Fluctuations in the CMB at large angular scales did not match predictions. Planck also confirmed what WMAP saw in terms of the asymmetry and the cold spot. Planck's final data release in 2018 showed more proof that dark matter and dark energy, mysterious forces that are likely behind the acceleration of the universe, do seem to exist. The future of the CMB. According to various cosmological theories, the universe may at some point cease expanding and begin reversing, culminating in a collapse, followed by another Big Bang, aka the Big Crunch theory. In another scenario, known as the Big Rip, the expansion of the universe will eventually lead to all matter and spacetime, itself, being torn apart. If neither of these scenarios are correct, and the universe continued to expand at an accelerating rate, the CMB will continue redshifting to the point where it is no longer detectable. At this point, it will be overtaken by the first starlight created in the universe, and then by background radiation fields produced by processes that are assumed will take place in the future of the universe. This concludes Buddy's video on the stages of the Big Bang, recombination, photon decoupling, and the cosmic microwave background. If you would like to follow along to see Buddy from Town become Buddy of Singularity, please click subscribe, and a like would be appreciated. Until next time, dear viewers, keep looking up and looking back, way back.